So I know a lot of you are, jeez, that's great. I know a lot of you are still thinking about the current homework, but if you're not, or even if you want to take a break or whatever, the next homework documents are out. We have the next round coming up. So if you want to take a look at those, start seeing what you're getting into with functional programming, genetic algorithm, and recommendations. So I want to give quick overviews of both of these. The genetic algorithm is somewhat of a machine learning technique, though it's not super sophisticated. We're doing machine learning proper that's beyond 116 at this point. But genetic algorithm is somewhat of a guess and check algorithm, where we're going to give it two functions in what I'm calling what's called an incubator and a cost function. An incubator is going to be some function that's going to take a list of doubles, which we're going to call genes, and then create potential solutions out of those lists of doubles. And then the genetic algorithm is going to work with these lists of doubles to be able to do its side of things. And then a cost function, which is going to tell us, given a potential solution, how good is it? We want the solutions with the minimal cost. A cost of 0 when we give a solution to the cost function means we have a perfect solution. That's the one that we definitely want to put out there. So the genetic algorithm, what this is going to do is take the incubator, create a bunch of random solutions, throw them all on the cost function, and then sort them by their cost. Take the best solutions, and then start varying those ones a little, start modifying their doubles, modifying their genes, start mixing them together, and then also create a bunch of more random solutions, and then repeat the process. Run it again. What's the least cost function? What's the least cost solutions? And then just keep iterating. Okay, let's look at those ones, and then just keep going until it starts converging onto a pretty optimal solution for whatever you're trying to solve. This works in a completely generic way. So as long as we have a problem we want to solve, and we can write a cost function that can assess a potential solution, and some way of generating solutions based on a list of doubles. As long as we can write those two functions, we can throw those into our genetic algorithm and have the genetic algorithm run its optimizations and try to find that nearly optimal solution. So this is a randomized algorithm with a lot of probability built in that based on its searching, it'll eventually find a pretty good solution. So what we effectively do is use the genetic algorithm to be able to solve problems without actually having to solve those problems. We just write the incubator, write the cost function, throw in the genetic algorithm, let the genetic algorithm do its thing. The genetic algorithm does have an expansion objective, and I have to warn you that not all expansion objectives are created equal. This one is pretty tough. So this one is doing some more, some deeper, I don't know what the word is, but you'll know what I mean, machine learning stuff, is using the genetic algorithm to train a neural network of your design. This is a tough one, so if you're just trying to get any application objective done, this might not be the best one, but if you are interested in machine learning at all, interested in programming AI at all, interested in that area, definitely go for this one. It'll be well worth the experience, well worth the practice of getting, of dabbling into this field. So definitely go for that. That one's out there for you. Recommendations also have, I'm like 90% sure this one's also going to have an expansion objective. We just don't have it all formalized yet. It'll be added to the doc once we get that ready. Recommendations is going to take a set of data of customers and products. We have about 475 customers and 35 products, and a big CSV file that says how many of each of those products did each of these customers purchase. And now with a new customer coming in with no purchase history, no information known at all about this customer, and they're looking at a page for one of these products, what other products do we recommend to them that they might want to buy because they're looking at that item page? So to do this, it's going to be a lot of statistics. It's broken down into 3 objectives. Given data that will be in a list of doubles, but there's some functional programming sprinkled in there to be able to extract properties. But given a list of doubles, compute the standard deviation given two lists of doubles, compute the correlation between them. And then finally, given a data structure of these properties of lists of doubles, basically the whole CSV sheet, and one of the items, how do we compute the top K correlated items, which are going to be the ones that we recommend? So what are the items that other customers typically purchase along with the item that you're viewing? And then give those recommendations to the user. So that's what we want to build with that one. And of course, with both of these assignments, no mutable state, no var. So how do we do both of these in a functional programming style of thinking? How do we do that with that restriction, forcing you into that functional programming way of thinking? How do we write code with the functional programming paradigm? So the docs are up. You can get a feel for what those are. We'll be adding to them. There's some of my wording and recommendations I want to work on. I want to give that a good pass and explain things a little better than I currently am. The videos will get up there, and the GUIs. We don't have the GUIs ready for either of these, so we'll get all that ready, and we'll be adding to the docs periodically. But if you want to start getting a taste of what is being asked, the objectives aren't going to change. What you're asked to do isn't going to change. We're still adding all the extra stuff to help you out with the assignments. But you can definitely get the full idea of what you're going to be doing during those. Okay, so with that, any questions about the homework, the structure, anything that's going on? Let's talk about recursion. Today's lecture, I'll try to go a little slower through today's lecture. Recursion is one of those topics where, I'll give my spiel, I'll tell you all about recursion and stuff, but it's one of those topics that just takes a while to sink in. So if you have any questions throughout today's lecture, this always applies, but feel free to, shout them out and ask questions where you have them to make sure that this has the proper time that it takes to just settle down in your brains and start making some sense. So I'll go through a few examples, explain everything that's going on with the examples, and then hopefully it makes sense. So the lecture question today is one that you've actually seen already, computing the factors of an integer. I only made one slight change to this one. The input of 1 should return an empty list. In the original question, I had it returning a list containing the value 1. I'm not sure why I did that in the original one. It doesn't really make sense. But I changed that, kind of fixed that, if you will, to return the empty list on this one. There's no unit testing being checked by Autolab because, well, you already have your unit test for this. Just make sure you update this one change and use the unit testing that you had before. You don't need Autolab to check your unit testing because I already did that the last time we had this question. I don't need to check you again. You already have those tests, so use those same tests to be able to test this that have already been verified through Autolab to be at least pretty good. And of course, banning var, banning state, no mutability, with, of course, obviously the intention being a recursive solution to this. It's a recursive lecture. So how do we write a recursive solution to solve the same thing that you most likely had an iterative solution for earlier in the semester? Okay, let's revisit this example. We saw this example earlier in the semester too. We got some flashbacks going on in today's lecture. We saw this earlier. I rewrote just a little bit of it. There was a var in this, and I want to make sure I don't have any vars in my lecture slides for these 2 weeks, because it'd be kind of wrong, I think, if I was using var and said, you can't though. So I rewrote it to get var out of there. And the only reason I used var before was because I wanted more variables on the stack, because we were using this example to talk about the stack last time. So I really didn't need that var last time either. But just a reminder, we're computing the geometric sum, which is going to be the sum of all the values from the input n down to 1. So when I say compute geometric sum of 3, I mean 3 plus 2 plus 6, or plus 1, and I expect the return value to be 6 from this method call. So last time we talked about this example, we had a focus on the stack. What is stack memory? What's a stack frame? what goes on the stack, things like that. Today we want to shift gears into talking about the recursive side of this. Last time I used recursion just to get a bunch of frames on the stack, and I didn't expect you to be able to write a recursive method. But now I want to use this example to show you what the thought process is behind designing a recursive method and how you're going to write your own recursive methods. How do you write your own methods based on this as an example? So we want to focus on the recursive side of things, of course. So first, we have our base case. Let's go through those steps from last lecture. We have our base case. Here I have n less than or equal to 0. I'm going to return 0, which I asked in the last lecture. We didn't know. Maybe somebody here knows what the expected mathematical behavior is for the geometric sum of 0. I'm saying it's 0, but I kind of just made that up. Or a negative number. What's the geometric sum of negative 10? I don't know if that's defined mathematically, but nobody's jumping on that. So we'll just go with it. I can get away with that one in this room. So I'm just going to say that the behavior is to return 0. Geometric sum of 0 or less than 0 is 0. So I could have easily had the base case be 1, and then I wouldn't have to ask that question. I could have said, if n equals 1, return 1. I know the geometric sum of 1 is supposed to be 1, and get rid of that. But regardless, our base case of our recursion is some trivially true input-output behavior. Some input where you just know the answer. Or you just make it up in my case. So it's something that's not wrong is our base case. If we don't hit our base case, and we'll have some conditional, some top-level conditional, if base case, else. If we don't hit our base case, we're going to hit our recursive step, or our recursive case. And this is going to be some logic, some code, where we end up making at least one recursive call. So in this recursive step, I'm making one recursive call to compute geometric sum, and I'm calling the method that I'm writing itself. So I'm going to make that recursive call in this step. If we don't hit the base case, there's at least one recursive call that's going to be made. If not, then that's actually a base case. You just have another base case. And when we're writing the logic for the recursive step, we're going to assume that our recursive call is correct. We're going to see why we can get away with that throughout today's lecture. But we're going to assume that compute geometric sum of n minus 1 is going to return the geometric sum of n minus 1. And then I want to write the rest of the logic. Okay, if I have the geometric sum of n minus 1, and I'm tasked with computing the geometric sum of n, how do I get there? Well, I'm going to add n to the geometric sum of n minus 1, and now I have the geometric sum of n. If I have all the values n minus 1 to n summed together, I add n to that, I got the values from n to 1 all summed together. So I'm just going to add n to the geometric sum of n minus 1, and if my assumption is correct, that my recursive call does return the correct value, then I am going to correctly return the geometric sum of n. So it's a big if, that's what we want to talk about, one of the big things we want to talk about, but that's how we're going to design the recursive step. We're just going to assume that the recursive call is correct. And then, critically important, we want to make sure that our recursive calls always get us closer to the base case. So whenever we make a recursive call, we need to make sure that eventually reaches the base case. If it doesn't, we're going infinite, we're blowing up the stack, we're getting stack overflow errors, and our program crashes. Nobody's happy when that happens. So in this case, I took an input of n. I know n is not 0 or negative because I didn't hit my base case. I'm making a recursive call. So n is 1 or greater. It's some positive integer. And I'm going to call compute geometric sum of n minus 1. So if I have a positive integer, my base case starts at 0, and I'm decrementing it by 1. I've satisfied this condition. I'm getting closer to my base case. If I make enough recursive calls, if my n is 10, I'm going to make a recursive call of 9, then 8, then 7, so on, until I get to 0. I will eventually hit my base case. So I say get closer to the base case. What I mean is through that chain of recursive calls that are going to be made for that original call, that chain eventually has to end at a base case. If it doesn't hit a base case, we just constantly make more and more recursive calls, more and more frames on the stack overflow, program crashes, no good. We got to reach our base case eventually. If our recursive call is always getting closer to our base case, we can guarantee that's going to happen. I shouldn't say guarantee, but we can pretty much guarantee that's going to happen. If we're always getting closer to our base case. So let's jump, and if all those pieces come together, so we have the base case, trivial input-output, a recursive step, sound logic based on the assumption that our recursive calls are going to return the correct values, and our recursive calls are always getting us closer to the base case. If those three things are true, we got our recipe for a great recursive method, and it should be working the way we expect it. Recursion will kick in and do its thing if we have those three things set up, and we're going to end up having a correct method that gives us the right values, the right return values that we need. So let's jump into the middle of the execution of this thing. Last time we talked about it, we were talking about frames on the stack. I'm going to assume you're good on that. We can jump to the middle, but I'll do a quick review of how we get to this part, this snapshot of the stack. So we're going to start with our mainframe. I just realized my slides say mainframe after so many times of doing this one. Anyway, we're going to start with the mainframe on line 10. That's going to call geometric sum of 3. It's going to create a new stack frame on the stack. And what we talked about this last time, but I didn't make it explicit on the slide. When main creates this stack frame and execution moves to this stack frame away from the mainframe is going to remember where it was executing. It's going to remember that it was on line 11, and specifically it's on this call of compute geometric sum that's sitting there waiting for that return value. And in the case of recursion, it might be waiting for a long time to get that return value. There's a lot that's going on before, but that that stack frame is sitting there waiting for that return value the entire time we go through this example. The next frame gets an input of 3, assigns it to its parameter. This 3 makes the base case false. We're going to get to line 5, call compute geometric sum, put another frame on the stack, 2, base case, false, another frame on the stack, and we got to this frame, base case, false, get to line 5, and we're about to put this next frame on the stack, which is going to hit our base case, and that's where we want to start talking about the recursion. So we got our recursion putting frames on the stack. Each one of these frames is assuming that this compute geometric sum is going to return the correct value for its input, and they're all sitting there just waiting on line 5 to see if they're going to get the right input. So let's put this next frame on the stack. We have an input of 0. Each frame is going to start at the beginning of the method, starting with the parameter, assigning that parameter the value of the argument, 0 in this case. We're going to hit our base case now. We're going to finally stop putting new frames on the stack. We're finally going to start popping frames off the stack and destroying frames and going back up the recursion instead of going infinite here. So our base case is true, and we're going to return 0. This is the last expression of the method. We hit 0. We're on line 3. We hit the end of the method, and our last expression was 0. So we're going to return 0 and destroy this stack frame. So our base case did its simple logic. Base case true, return 0. Now we get to go back up the recursion. So we're going to return 0. This frame was waiting on line 5, so we're picking up execution where it left off. It was waiting on this call of compute geometric sum to return. Compute geometric sum of 0. Return correctly 0. It's the base case. Of course, it's correct. So in this frame, our assumption that the recursive call is correct is trivially true because the recursive call, the input of the recursive call was a base case. Base case, by definition, should be trivially true. It should be easy to verify. The base case is true. So we got that value of 0. Our n is 1, so we're going to add 1 plus 0 and return that to the next frame. Our input was 1. The geometric sum of 1 is 1. So we can start seeing our logic apply based on that assumption. We had an assumption that this was correct. It in fact was correct because this was the base case. And then we're going to run our logic. Okay, I have the geometric sum of 0. I'm computing the geometric sum of 1. I'm going to add 1 to it and return 1, which is the correct output for that input value. So I'm going to return 1 back to this next frame. I'm going to keep repeating this process. Return 1. This frame gets the value of 1 from its recursive call. So it said compute geometric sum of 1. And it said I'm just going to believe that whatever you give me is going to be the correct value. And it happens to be the correct value. We got the value of 1. So that assumption was correct in this case. And it's correct because that 1 was computed based on a recursive call that got the base case. The base case was true. Our logic was sound. So we computed the correct return value of that second to last step of the recursion because the base case was true and our logic was sound. Return the correct value. Well, now our assumption was true based on that. Our logic is still sound. The geometric sum of 1 was returned, which was 1, and we're going to add 2 to it. So we're going to compute 3, which is the geometric sum of 2, and we're going to return that back to the next frame. That next frame is waiting on line 5. It has an n of 3, and it called compute geometric sum, just assuming that it's going to return the correct value. And it is, in fact, going to return the correct value. It's going to return that 2 plus 1, 3. We're going to add 3 and 3, and correctly return 6 from that frame. So we were assuming that our recursive calls are going to be true. They're going to be correct. And that assumption is true for the base case. So if we start thinking of our recursion the other way, instead of thinking from the top call down, if we think from the base case up, we can start seeing why that assumption is true. It's because we're starting with something that's trivially true. We return something that's trivially true, and then run our logic. If our logic's sound, and our assumption is trivially true for that second to last recursive call, our logic is sound, we have something that's accurate, we're going to run our logic and return something that's also true or correct, or the correct return value. And then the next step is going to get that. It's going to run the same logic and return something that's correct. It's just going to run the same logic and return something that's correct, which is going to run the same logic, return something that's correct. So all our assumptions, as long as our algorithm is designed well, all those assumptions just end up being true as long as we're arriving at the base case, returning the correct value from the base case, running some sound logic, and then returning a new value based on whatever that logic did. In this case, adding n to each of the return values. So we start with 0, return that, add n, return that, add n, so on and so forth. Then when that frame returns, we get 6 back to the main method, and our program gets to run business as usual. So this variable result is finally created to store the result of this, to store that 6. We can print 6 to the screen, and we got our correct geometric sum of 3. Are there any questions on this example? I guarantee this is about as boiled down as I can make a recursive example. So if you have any questions on this one, please ask, because any other examples you're going to see are going to be more complex. The next one is going to be anagrams. Yes? Sorry, can you speak up a little bit?
Because it's returning the base case at the end of the execution of the kind of function, how do we use the
value of the geometric sum. Do you mean in the main method? Like how do we get this value? So we're only returning 0 on this last step of the recursion, this last recursive call that hits the base case. So only on this last recursive call was the input 0, where this is true, and then we get the 0. And then when we return 0, that returns 0 to this next frame, which takes 0 and adds its value of n to it, which is 1, returns that. The next stack adds its value of n to it, which is 2. The next frame adds its value of n to it, which is 3, and then it's finally 6 that ends up being returned to the main method. And this is part of the. I'll actually talk about this a little more for the next slide, but I do want to talk about it here while it's up here. Is the base case is actually the only spot where we're creating a new int, and on the recursive steps, all these other calls, we're not really creating anything more. We're only returning 0 ever, and then we're accumulating that later on. So we can think of this back to 115, the accumulator pattern, where we say or I guess Python, we didn't even have any variable declarations, but like x equals 0, and then say we want to sum up all the values of a data structure, iterate through that data structure and keep adding each value to x, and then x is going to accumulate the total answer, then we can return x. We're doing the same thing here, but we're doing things a bit backwards, a bit different order and things. We're getting down to our base case, and our base case is what's going to initialize our accumulator variable in the same way. And then as we go back up the recursion, that's where we're getting all that summation going. That's where we're adding all these values to it, and finally returning that value with all of that accumulation that it got from coming back up the recursion. So the base case initializes, and then as it comes back up the recursion, it's accumulating all that information. No more questions on this one? You're all ready for anagrams? Let's talk about it. Let's go to it. So with this, just off the bat, there's a lot of functional programming stuff in here. I wanted to get rid of all the vars, like I mentioned earlier. The whole reason for me to ban var is to force you into a functional programming way of thinking. So when I rewrote this without var, I just naturally had to use a lot of functional programming stuff. A lot of this will make more sense on Monday, though I will have a few slides at the end of today's lecture where I'm going to talk about the functional programming stuff that I used here and talk about it just very briefly. So for now, you have to just kind of take my word for it that this is doing what it's supposed to do, but I will review it, we'll talk about it. But if this doesn't make sense to you right off the bat, well, it shouldn't unless you've studied functional programming on your own at some point. There's no expectation that you can read this code right now, just to make sure that's clear. Though some pieces you should be able to pick out. Some of this is the same as the last time we saw it, but like you're not going to understand what this is, what these do, unless you've studied that on your own at some point. So just to get that out of the way, let's talk about the recursive setup for this anagrams method. We saw this earlier, but I was like, this is recursion. You'll learn about this later. Now is later. So let's go through the same steps that we saw with our other one, with our geometric sum, and talk about how it works in this anagrams application. So first, our base case, some trivial input-output behavior. If an input string, and just a reminder, we're taking a string and then returning a list of all the strings that can be made by rearranging the characters of that string. So we want to compute every anagram of that input string. So that if the input string is of length 1, there's no way we can rearrange the characters of that string in any other way. It is itself its only anagram. So throw it in a list and return that list. And this is the same with the last one. This is the only, so our ultimate goal is to return a list that's going to have all these anagrams of some arbitrary string. But our base case is the only time we're actually creating a new list. We're creating it with just one element. And then as it comes back up the recursion, that's where we're going to start combining lists and start expanding their sizes and getting all the anagrams in there. So base case, trivially true. I actually have a second base case in here that's hidden, it's implicit. But I do technically have a second base case. If you have an input that is the empty string, which is something that needs to be handled by, if you're going to handle strings, you got to handle that case. This loop is going to iterate over all the characters of the string. If I have the empty string, this loop doesn't do anything. I don't execute this loop at all. And through all this stuff, I end up returning an empty list if the empty string was my input. So I do have a second base case. I do have that edge case covered. If somebody does give me the empty string and says, what are all the anagrams of the empty string? I handle that as I should. This should return, should at least have defined behavior. In this case, I'm returning the empty list. I gotta have my slide. So yeah, this is the only time a new list is created. Only in the base case. So each base case call creates a new list. And as we go up to recursion, we're adding to these lists. We're combining these lists to be able to get the overall answer. And the recursive step. So a quick reminder of what we did last time. Even though it's rewritten in functional programming, using the functional programming paradigm, is what we're doing is iterating through the characters of the string, removing each character one at a time to create this new string. And this line here is verbatim from before, from last time. Splitting up that string, we're going to get that, create a string with that one character removed, make our recursive call on that string, on each of those strings with each character removed. And then when we get the anagrams of that, we're going to just assume that this call is correct. And then we're going to append that character that we removed to the end of all the anagrams of that string with the character removed. And then we're going to take all of the recursive calls, each recursive call, combine all those strings into one, remove the duplicates. That's what this last part's doing. So we make this one recursive call. This is where we make the recursive call. For each character in the input string, we're making a recursive call. So if our string's length 10, we just made 10 recursive calls throughout this loop. So we have a lot of recursion going on here. So this is the only place we make a recursive call. And we're going to assume that it's going to give us all the anagrams of that new string that we give it, and then build all our logic based on that. So if this does give us all the anagrams of new string, then I want to append that character I pulled out to each of those anagrams, and I want to combine, for each of those characters that I iterated over, combine all those anagrams with the character appended to the end into one big list, and then return that. If my assumption is true, that logic is sound, and if you believe me that this code is doing what I say it's doing, then we're going to have a successful recursive step. Not all the way there yet, but we are going to have a well-designed recursive step. We have a solid base case that's trivially true. A hidden base case I should put if input.length equals 0, return empty list, just to make that explicit, make that more clear. And then I need one more piece to this. The third piece, the third ingredient for our successful recursion, is going to be making sure we always get closer to the base case whenever we make a recursive call. Our base case is either input of length 1, the hidden base case input of length 0. Those are my two base cases. I can't have a negative length. That doesn't make sense for a string. So if I'm hitting my recursive step, if I'm making a recursive call, I know that I have a string of length 2 or greater. And when I make my recursive call, I'm taking that string, removing one character from it, and then making the recursive call on what's left. So whenever I make a recursive call, I must be making a call on a string that is length 1 less than the length of the input string. So if I'm always decrementing the length of the strings for my recursive calls, I'm eventually going to get to my base case of length 1. I'm eventually going to get there because I have to be greater than 1 if I hit a recursive call, and I'm going to decrement until I reach 1, until I hit that base case, and then the recursion can start returning, the base cases can return, my recursive steps can start doing their logic and start returning values back up the recursion, back up the stack. So I have the 3 ingredients for successful recursion. So I should have a successful algorithm here, a successful method. So just like we saw with compute geometric sum, the action actually starts happening from the base case. It's tempting to start thinking of recursion as starting with some large input, some long complex input, but the real work starts happening at the base case. So if I have a base case and these length 1 strings returning, when I have a length 2 input string, that's where we can start seeing how this starts to come together to be able to make things work. So if I have some long string as my original input on the top level of the recursion, let's jump down to the base case and see what's happening down there. When we have an input of size 2, we have just 2 characters left in our recursive call. That's going to make 2 recursive calls on each character. So I'm going to remove A and make a recursive call on T, and I'm going to remove T and make a recursive call on A. Both of those are base cases. I know I'm getting the right answer. The only logic is length 1, yup, return it. So I know those are going to be true. So in my recursive calls of length 2, I made 2 recursive calls, got the correct values because they're trivially true, because they're the base case. I'm just returning a list with the input. And then when I get the return value of A, I'm going to take the character that I removed, which was the T, and append it to the end of it. And when I get the return list containing just T, I'm going to take the character that I removed, which was A, and append that to the end of that. Now I have the list containing AT and TA, which are the anagrams of at, and I'm going to return that up to my call of length 3. So in my call of length 2, I can assume that I'm going to get the right answer because I'm making recursive calls to the base case. But look what just happened when we had our recursive call of length 3. It's going to make 3 calls just like this, following this logic of recursive calls of length 2. And we can follow this logic and see that that recursive call of length 2, based on the base case being correct, they are going to return the correct list of anagrams. So my recursive call of length 3 is getting the correct value from all these recursive calls of length 2. Then my recursive calls of length 3, they're going to run through similar logic. Append each of those 3 characters that were removed, append that to each value of all the lists that are returned, combine all those into one list, and then return that back up to a recursive call of length 4. The recursive call of length 4 gets all these 4 calls of length 3, which are correct by our logic, and then we can just keep repeating the process. Well, from 3 to 4, our logic is sound. From 4 to 5, our logic is sound. From 5 to 6, our logic is sound. We could just keep going up. So even though when we design our algorithm, we're just assuming that our recursive call is going to be correct, as long as our base case is correct, and our recursive calls always reach the base case, and our logic is sound once we get those recursive calls returned and combine them in the correct way to be able to return a correct value, as long as we have those 3 things, that assumption isn't an assumption at all, it's going to be correct. Any questions at this point? Okay, so let's talk about these functional programming words. Let's briefly talk about each one. Yield, possibly, I don't know, maybe the coolest one. Maybe not, I don't know. It's a cool one though. Yield is going to work with loops. So when I have a loop here, I have a loop inside some other syntax. It's kind of crazy looking, right? So what is this doing? I have a loop that I'm setting up. I'm going to iterate over some data. I'm going to put the word yield right in between the setup for the loop and the body of the loop. When I put that yield keyword there, what happens is instead of iterating through the data and just executing the body of the loop for each element of the data structure that I'm iterating over, Yield is going to take the last expression to be evaluated in each iteration of the loop for each data element. Take all those values, similar to if these were function calls and taking the return value from the body of the loop, similar to that. Take all of those values and throw them in a data structure and create a data structure with all those values. So we can write loop syntax that's going to create a data structure based on the last expression that's evaluated in the body of that loop. My last expression here is a list of strings. So it's going to create a data structure of lists of strings. Scala's going to attempt to match the type of the data structure I iterated over. This is a range, so to be honest, I don't even know what type. I mean, we can't have a range of lists of strings. I don't even know what type we get out of this. Probably some general sequence. But whatever we get, I'm going to convert it to a list. So I'm going to put this entire thing in parentheses. I get some data structure of lists of strings containing all these lists of anagrams for each character that I removed. Create that whole thing, turn that whole thing into a list, and now have a list of strings containing all those anagrams based on each character that I removed, which happens to be all of the anagrams for this input word. Map. I told you I'm appending the characters to each element, but what is this really doing? This is very similar to your lecture question on Monday, this Monday that we already had, not next Monday, where you took a list and a function and returned a list which was all of the elements from the original list with that function applied to them in that new list. That's exactly what map does. That's why I wrote that question like that. So that's what map does. It's going to work with the data structure, call it on the data structure, give it a function, and create a new data structure with all those elements, but with that function applied to it. So I'm appending that character to each element. And the function that I gave it, we could use the same syntax that we used earlier, but we actually have an opportunity to shorthand the syntax a little bit. So I thought I'd show you a neat Scala syntax thing here, is if we have a function that takes one parameter and the type of that parameter can be inferred, then we can use this underscore syntax. Instead of saying s of type string, and then our big arrow, our equals greater than, and then the body of the function, instead of using that syntax, in this case, the type can be inferred because this is a list of strings. Map is expecting a function that takes a string based on that, takes one parameter, and that parameter is a string, so it knows the type that it's expecting. When it can infer all that, we can just use underscore as though underscore were the name of the input. So we don't have to specify the type, the parameter lists, or have that arrow notation. We just do underscore, and underscore is in place of the name of our variable. So underscore represents each string in this data structure, and then for each string in the data structure, append that character to the end of it, and create a new data structure based on that. So I converted this list of strings into a new list of strings, which is the same list, but with that character appended to the end of each word, or end of each string, not necessarily words, end of each string in that original data structure. And then a couple useful things. The Scala data structures have a lot of these methods. These are just the two that happen to be most useful for this particular application, but the data structures in Scala have a lot of these very quick but powerful methods. Here I'm calling flatten, which is going to take a two-dimensional data structure, and as the name implies, flatten it into a one-dimensional data structure. So I have a list of strings. Flatten is going to convert that to a single list of strings containing all of the strings from all of the lists inside the original list. So I get that as just one list of strings containing all of the anagrams I just computed. And then distinct is going to remove the duplicates. So last time we had to check if this is in the list, don't add it, but if it isn't, add it. We had that logic to remove the duplicates. Now we just say .distinct. And one of the themes we're starting to see here, we'll definitely see more of on Monday, is that with functional programming, we're much more we're much more descriptive in our code. It's a much more descriptive way of writing things. Whereas with procedural programming and object-oriented programming, we're usually explaining to the computer how to do something. When we have the accumulator pattern, okay, how do I accumulate this variable? How do I find the max? Okay, well, you set some min value, you iterate through the data structure, you check if the value I'm looking at is greater than, is less than min, I said max, I'm getting it mixed up, but you know what I'm talking about there. We're really explaining how to do something. With functional programming, we're much more concise, and we're more describing what we're doing. I want to take the anagrams of this string and map those based on this function to a new data structure. I want to take this list of strings, I want to flatten it, and then get only the distinct elements out of it. We get to be much more expressive and much more descriptive in our code. Instead of saying how stuff happens, we're just saying what we're doing. What am I doing with this? I want to yield the values from this loop. I'm not just writing the code to do that. Okay, give me a new empty list of strings, and then iterate through, and then keep appending to it. That's how we do that. Functional programming is more, what are you trying to do? Call the functions that say what you're trying to do.